Hi, and welcome back. We are going to do a lecture today on section 5.4, which is really an extension of multiplying polynomials. However, we're going to get into some special products today, which help us with a little bit more with definition or defining our polynomial multiplication. All right, so that being said, I want to just recap the process of FOIL. Remember, if you have two binomials, binomial times binomial, you can use the process of FOIL so that you use the first terms to multiply the outer terms, the inner terms, and the last terms. That is your FOIL process. Now, in this particular situation, just making my parenthesis a little bit darker there because it was looking a little light, a little thin. If I were to use FOIL in this process, let's go ahead and see what happens. So I have x times x is x squared. X times negative y is a negative xy. Y times x is a positive xy. Remember, I'm going alphabetically, so y times x is the same thing as xy. Y times y is going to be y squared, and that is positive and negative, so that is a minus y squared. Now, through our process of FOIL, we got our first term, we got our outer term, our inner term, and our last term through multiplication. At this point, you need to see if anything can combine. I do have these two middle terms right here, which are like terms. They're both xy's. And because they are positive and negative with the same coefficient, they actually cancel out, which gives me a special case of x squared minus y squared. This is also known as the difference of squares. Now, the difference of squares is extremely important. And the first time you learn it, you really want to understand the definition holistically, meaning you know that if you can identify two binomials that are exactly the same with one difference, one is adding, the other is subtracting, that you will be looking at a difference of squares situation. What that means is you can actually skip the multiplication step because you know those middle terms will actually cancel out, and you can go straight to a definition. The definition being, quite literally, just to simplify what we've just done, x plus y times x minus y will always come out to x squared minus y squared. This is your actual definition for the difference of squares. So let's see how it's actually applied. Assuming we have that first example of 8r plus 1 times 8r minus 1, making sure I wrote it correctly, what we could do is either FOIL, or we can identify that we have the same exact set of binomials with one small difference. One is adding, the other is subtracting. This is also called a conjugate. Just to get that terminology out there, they are conjugates, meaning one is exactly the same as the other, where one is adding, the other is subtracting. Again, the term conjugate. Now, in this situation, according to my definition here, my x squared is my first term squared. So I have 8r squared. My last term is my last term squared. So minus 1 squared. So according to the definition, without having to do all the multiplication steps, which this is a simple example to do that with, but going through the definition, I would get 64r squared minus 1. That would be my solution from the difference of squares here. Let's just prove it. Let's see what happens if we were to actually go through the multiplication process. If I were to FOIL, I have 8r times 8r, that's 64r squared. 8r times negative 1 is a negative 8r. 1 times 8r is a positive 8r. 1 times negative 1 is a negative 1. My two middle terms will cancel, so I'm left with 64r squared minus 1. These are exactly the same. Meaning if I go through and do my FOIL process, or if I use my difference of squares definition, they come out exactly the same. Now, you might be saying, okay, why does it matter to use one over the other? Well, the more you introduce additional steps into your problem solving, the more chance there is that you might lose something along the way or miscalculate. So having a definition available really helps you to simplify your processing, mental processing, as you're going through and working on that math. This will also come up much later on, so you definitely want to know this definition. Like, big hint, it's going to be everywhere, because difference of squares will help you as you start factoring later on. That being set aside for right now, let's go through and try another example. This next example, I got plenty of space up here, so I'm going to work with it. I have 2x minus 7, 2x plus 7. So in this next example, again, I have conjugate binomials. I have conjugate quantities, 2x minus 7, 2x plus 7, meaning they are exactly the same, with the only difference being one is added, one is subtracted. Now, going straight from the definition, I have my first term squared minus my last term squared. That is my definition from difference of squares. This gives me 4x squared minus 49. Excellent. Let's try another one. I have 9x plus 2y squared, 9x minus 2y squared. Now, these are conjugate values. I have 9x plus 2y squared, 9x minus 2y squared. They're exactly the same. One is added, one is subtracted, so they are conjugate values. Let's go straight to definition. So I have 9x squared minus my 2y squared squared. Now, again, remember I said exponent rules will haunt you forever. Here they are. They're popping back up. So let's do this simplification first. I get 81x squared. Remember, this is your power rule. So what you're going to do is get your 4y to the fourth, multiplying those exponents. You are subtracting here. So you have 81x squared minus 4y to the fourth. And that's it. Now, difference of squares is extremely easy to work with, and it's very easy to identify once you start getting into looking at the multiplication. You're just looking for conjugate values. Let's go into another rule that doesn't necessarily, it helps you out quite a bit with mental processing, and it is something that you will need for identifying in factoring. But it's not necessarily as intuitive as difference of squares, in my opinion. So that being said, this is called a square of a binomial. So I have x plus y squared. Think back to your definition of exponents that we talked about a couple lectures back. If you have something raised to an exponent, you're simply taking that base, whatever it happens to be, and multiplying it against itself that many times, whatever the exponent happens to be. In this case, I have a base, which is x plus y, so it's the entire quantity, and it is raised to the second power. So we are going to derive this rule, if you will. So this is technically saying x plus y times x plus y. Now this is very different from the difference of squares that we just covered, because these are not conjugates. This is x plus y, this is identical x plus y. So they are not conjugate values, they are identical binomials. At this point, let's go ahead and just FOIL. So I get x times x, which is x squared. X times y is xy. Y times x is xy. Y times y is y squared. Combine my like terms. I get x squared plus 2xy plus y squared. Okay. Now, let's try it if we were doing a difference. So I have x minus y as a quantity squared. Same exact idea. It's that base multiplied against itself. So they're identical terms. They are not conjugates. They are identical terms. Foiling, I get x squared minus xy plus y squared. Because negative times negative there is positive y squared. Combine your like terms. I have x squared minus 2xy plus y squared. What's the difference between this solution and this solution? The only thing that you can see is the sign. Now check this out. What was your original sign in this problem and this problem? This sign was positive, and the solution came out positive. This sign was negative, and this solution contained a negative. So what we are looking at here is that the square of a binomial can be very easily determined from the binomial without actually doing much work. So we can determine the solution by definition. This is one definition right here for the difference. This is one definition for the addition or the sum. Now, these two definitions, as you start getting into factoring, will actually help you a lot. However, right now, especially as you're trying to go through and focus on different rules, I highly suggest focusing on the difference of squares rule. That's the one that you really need to get a lot of practice with. These will start to fall into line as you start doing more throughout the process. That being said, let's try a couple examples just to see what we get. The first example that I have is 3r minus 5s squared. By definition, we are using the second definition, the difference, for our square of binomials. By definition, I know that I have my first term squared minus 2 times my first term times my last term plus my last term squared. Now you might be saying, whoa, slow down. Where are you talking about getting first and last and whatever? Go back to the definition. My first term is x, my last term is y. That is consistent in both of these definitions. When I'm looking at my solution for that definition in either situation, I have my first term squared. So my first term is x, I have x squared here. I have 2 times my first times my last. So I have 2 times my first term, which is x, times my last term, which was y. The sign on this 2 is where it comes back to this original definition. If the binomial was negative, the sign is going to be negative. If the binomial was positive, the sign is going to be positive. And then my last term is y, so my last term is squared here. And that is always going to be positive. Now, that being said, going back to our problem, I have my first term, which was 3r squared. I have my 2 times my first term, which is 3r, times my last term, which was 5s. This was a negative, so this is a negative 2. And then I have my last term, which is my last term, 5s squared. Okay, let's go ahead and work that out. That's 9r squared minus 2 times 3 is 6, times 5 is 30, RS, plus 25 S squared. That is 25. Make sure my 5 looks a little bit more like a 5. There you go. And that is it. That is the simplified version from definition. Now you might be saying, what? That seems way too hard. Again, this kind of rule, as you start doing more of them, will fall into line. It will make sense. What happens if you didn't use the definition? What happens if you just go with the strategy of, I'm just going to FOIL this? Same exact problem. If you were to just FOIL this out, you would expand it. If you're planning to FOIL, you must expand. That is a very, very important point. Now, here I have my expansion. FOIL, I got my first term, which is 9r squared. My outer term, which is a minus 15rs. My inner term, minus 15rs. My last term, positive 25s squared. Combine my like terms. I get 9r squared minus 30rs plus 25s squared. This and this are exactly the same. So if you're not getting the definition right off the bat, just go back to FOILing. It's easier that way if you need to see it step by step. The definition is just meant to save you a few steps. That's all it is. Now, let's try another example. And I'm going to strictly use the definition here. Don't worry, because I am getting board space. You have the definitions written on the top of your notes. So simply refer to those definitions. Or if you've already written them in your notes, you have them as well. But my next example is 8x plus 5. This is a quantity squared. By definition, I know that I'm going to have my first term squared. I'm going to have plus, because this is a positive, plus 2 times my first term times my last term, plus my last term squared. Simplifying this gives me 64x squared. I have 2 times 8 is 16 times 5. I'm going to have 80 here. X, 80, 80, x, plus, this is going to be 25. And that is all. That's it. Now, I want to point out one thing that is extremely important. And you see this note on your paper. It's kind of small. It says caution. And it says that x plus y quantity squared does not equal x squared plus y squared. Let's talk about that. Why is that note there? Well, if you were to look at x plus y as a quantity squared, you're actually talking about that particular definition being expanded. You're talking about x plus y times x plus y. That's what this actually means. And so when you solve this out, that's where you got the x squared plus 2xy plus y squared. So by expanding this and then FOILing, you can see where this definition comes from. It is not ever simplified to x squared plus y squared. This is a big mathematical no-no. Don't do it. Okay, let's get some more board space here. I'll go ahead and erase this side too. Let's get a couple more problems up here. Get some practice with it. Here we are. Okay, so my next example, I have 3x cubed times x minus 4 times x plus 4. And you get the instructions for these types of problems usually like simplify or multiply. Now, in this example, how many of you, by a show of hands, keep in mind this is a video recording and I cannot see your hands, but if you have it up anyways, that is great. By show of hands, you have 3x cubed times x minus 4 times x plus 4. How many of you are thinking, distribute? Yeah, it's pretty intuitive. You want to jump into multiplication right away. However, this is where it's very important to slow down and look at your problem. Remember, you can multiply in any order. Looking at my binomials here, I can see that these are exactly the same, the only difference being one is added, one is subtracted, meaning these are conjugates. And what do I know about conjugates that multiply? Those are the difference of squares. So I know right here that I can jump straight into the difference of squares definition. So I have 3x cubed, that just came down, nothing happened. This simplifies. I get x squared minus 16. That's your difference of squares being simplified. Remember, it's that first term squared and that last term squared. And you're always subtracting, hence difference of squares. At this point, you can go ahead and simplify. So we're going to go ahead and distribute. We're going to have 3x cubed times x squared is 3x to the 5th. 3x cubed times 16, negative 16, so that's a negative, just bring it down. 3 times 16, you get 48. X cubed. That's it. That's all you've got. So always stay cognizant. You're looking out for anything like conjugates. That's your big one that really shows up and is like, bam, difference of squares, use it. Let's try another one. I have m cubed minus 3 times m cubed plus 3. Yep, okay. Now at this point, I'm looking at my problem. They're conjugates, difference of squares, use it. So I have m to the 6th, because it's those two. Those are my terms, so my first term squared is m to the 6th. And then I have 3 squared, which is going to be 9, and I am taking the difference of those, hence difference of squares. All right, beautiful. Last example for this section. So I have 3 times the quantity of m minus 4p squared. Now, as you're looking at this particular problem, keep in mind that what we're looking at is that this base is squared. So there's a couple approaches. You can use the definition for the square of binomials, or you could just expand it and multiply out and see what you get. So I'm going to leave that method really up to you, but I will do the fully expanded version because I know some of my audience will prefer that version over using the definition right away, and that is okay. So I will expand this just to show a strategy that you can use. Again, you can use the definition. I encourage you to start using those definitions to get practice with them, but especially focus on difference of squares. Now, for this problem, you would use the square of binomials definition, or you could just expand it like what we're doing right now. Now, I'm going to go ahead and simplify this section first. I'm going to come back to this 3, so I have 3 times whatever I get over here. M times m, I have m squared. M times 4p minus 4mp minus 4mp plus 16p squared. I have 3 times of just bringing it down. Combining my like terms right there, I have m squared minus 8mp plus 16p squared. There's no other like terms here, so I'm going to distribute that 3. That gives me 3m squared minus 24 mp plus 48p squared. That is all that you get. Okay, so ladies and gents, that concludes section 5.4. We will be continuing into another lecture momentarily or as soon as you click play.